Alright guys, so this will be a shorter video. This is just to introduce you to logistic functions. Alright, I want you to take a look at this data here, which is the progression of men's high jump world record by year. Alright, so you can see how the high jump world record increased slowly, right, and it increased a little bit quicker. Then it leveled out, and then it started increasing again, and it kind of got to almost some type of limit, like maybe they can't jump higher. Now, it's interesting if you go and look at the history of what's going on here. There's several things that happened, right? One of the flat spots is when one of the world wars happened, right? And so there was a time period when the high jump record didn't change much because not everybody was participating. There's also a point where the height shoots up. That's because they started the Fosbury flop. You know, the Gene Fosbury, I think Gene was his first name. His last name was Fosbury anyway, and he's the guy that started jumping over the pole backwards by using his center of mass to be able to actually jump higher by jumping backwards and curving his body. So anyway, a lot of interesting things in the history here that give some context to it. But what I want you to see is that this function here is an interesting function, right? It looks almost like we have some type of curve here, like some type of exponential curve. We definitely have some linear pieces, right? It feels like maybe it could be linear here, feels like maybe it could be linear there, right? But overall, this is kind of what we have, okay? We have a curve that starts down here, and it's curving up until it gets to some point, and then it feels like it's kind of curving out there, and almost as if there's some type of asymptote here that can't be crossed, okay? Whether it can be crossed or not is then a debate that could happen at a later date. However, this is called a logistic curve. A logistic curve is one that very often has some type of asymptote in the beginning and also has some type of asymptote at the end. This is often called the carrying capacity. Okay, and the carrying capacity is just a value that the line won't be able to reach, right? It could be population capacity, that you get to a certain point where the population can't grow any further due to physical restraints or due to the food that they have to feed the population, whatever it may be. There may be some type of limit. Okay, this carrying capacity, you'll see the equation up here is L. Okay, and we'll look at that in an example in just a moment where we'll see how that kind of comes out to play and why that works out the way that it does. Okay, in this logistic function, you will have a 1 here, you'll have an exponential function here with a negative, and then your x will always be in the exponent there. Okay, here's your y value, and all of these other things, the L, the C, the K, those are all constants. They all have to be positive constants that allow us to get this kind of curve where it's increasing, but then at some point it slows down as it reaches that carrying capacity, okay? It's also likely that there's, I mentioned it before, that there's some type of asymptote down here. Now, depending where on the graph we actually start seeing the graph, you may or may not actually see that asymptote, but we'll talk about that one in our example here in just a moment as well. All right, so that's kind of an introduction to a logistic curve, giving you an idea of what it looks like and some of the pieces. Okay, what I'd like to do now is just look at an example. Okay, here's an example. You've got a function that models percentage of people globally with access to broadband internet with respect to time given by the logistic function. Okay, they're not giving us a year when this is starting, but it's unimportant. We want to see how this looks. Now that should make sense. In the beginning, very few people get broadband internet because it's expensive, and as time progresses, it becomes marketable to the masses. Lots more people are able to use it. Therefore, it gets cheaper, so more people buy it until eventually almost everybody has it. At that point, it's not going to increase very much anymore. This is a good example of a logistic function. Now, you'll see that this matches very closely to the equation that we had before up here. F of x equals L over 1 plus C e to the negative kx, right? You've got f of x equals L over 1 plus C e to the negative kx. And all those pieces are there. You've got the L, which is 100. You've got the 1. You've got the C, which is 10. And you've got the K, which is 0.5 here, right? And then, of course, x is time, which is your independent variable. Okay, now the first thing it wants us to do is sketch a graph of this function. Okay, now you could easily plug this into your calculator. In fact, I invite you to do that. But I want you to recognize a couple of things just really important as we begin to draw this graph. Okay, the first thing is this, the L. Remember, the L is the carrying capacity. That's 100. Now that makes sense because P represents the percentage of people that have access to broadband internet. The maximum that can be is 100%. That's carrying capacity. So up here at 100, I should have some type of asymptote that I'm going to approach. All right? Now, the other point that's probably really important is getting the y-intercept. You could put 0 in for t. So I go 100 over 1 plus 10 e to the negative 0.5 times 0. Okay, this, of course, would continue to be 0. E to the 0 would be 1. So I'd get 100 over 1 plus 10. Okay, now 100 over 11 would then give me a value of 9.09, which then would be my y-intercept down here. So this would be 0, 9.09. Okay, so from there, I do know that this will be a logistic curve, and so it should look something like this. If you get it on your calculator, you should be able to get some of the x values in the middle here if you want. All right, so I've moved the graph up out of the way a little bit so that we can talk about the rest of these questions. So letter B is write down the range of values of the function and interpret their significance. Okay, well, the maximum that it goes is 100. So the range has to be less than 100, not equal to, because it's not going to get there according to a logistic function. It's realistic. There are some people that just won't ever be able to get the internet. And then, of course, starting at time 0, the lowest possible number here is 9.09. So whenever we started taking the data, 9.09% of the population already had broadband. All right, so there's your range. Not too bad. It's just interpreting a graph, just like all the other graphs that we've done. Okay, then we're going to use the model to predict how long it will take for half of the people to have access to broadband internet. Okay, so that means we want the percentage to be 50. And so we just put 50 equals 100 over 1 plus 10 e to the negative 0.5 t. And that you can put straight into your calculator. You can solve it. Hopefully, double check, but hopefully you're able to get that t equals 4.6 years. Okay, that's just a simple solve. Okay, another way that you can do this is you can put the original function in as y1 in your calculator, or f of x1, depending on what your calculator, how your calculator does that. And then you can put 50 in for your second line. You could do a function 2, f2, or y2, and have it put in 50. And so that would be your second line. And then you can find the intersection. And the intersection should be 4.6 years, which is what we got there. Graphing is the way that we used to do everything before we had solve. We just had to learn how to deal with graphs and find intersections and things like that. All right, so we've got the model to predict how long it will take, 4.6 years. And last of all, we've got letter D, calculate the percentage of people who will have access to broadband internet in 20 years. And this simply is to take the function P of t and find out what 100 over 1 plus 10 e to the negative 0.5 times 20 is. And you work that out, beep, 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 put it in your calculator, and you should get about 99.95%, okay, which is showing us getting very, very close to our asymptote of 100 here. Okay, now one thing I do want to look at is why does that carrying capacity, why is it 100? Why does that number work? Okay, well, I want to show you. Let's take PT equals 100 over 1 plus 10 e to the negative 0.5. What would happen if t got really, really big? Okay, say t was infinity. All right, that means that you're going to have here 100 over 1 plus 10 times this e to the negative something, right? This is going to be a very, very large number. Remember, the negative means that you can rewrite it as 1 over e to a very large number, okay? When you divide the 10 by this very large number, this term right here is essentially 0, which means that I get 100 over 1. I'm never going to quite get 100 over 1 because this is never actually going to be 0. It's going to get really close, but it's never actually going to be 0, which is why I get really close to 100. But because I always have 1 plus some really tiny number, I always have something slightly less than 100. All right. The other thing that I wanted to look at, let's go back, is what would happen as we go back the other direction, go back over to the left. All right. So in this case, we're going to take 100 over 1 plus 10 times e to the negative 0.5. And this time we're going to go to the negative infinity, right? So we're going to go back this direction, okay? Because I want to show you the asymptote of the other end. Okay, well, what happens when I multiply the negative by the negative? Well, I get 100 over 1 plus 10 e essentially to the infinity. So I get 1 plus a huge number here. And so when I do 100 divided by 1 plus a huge number, let's say that it's even, I mean, this isn't anywhere near to infinity, right? But let's put in 100 million. What would happen if I add 1 to 100 million? Well, I'd have 100 million and 1. And what would happen if I divide 100 by that number? I get a number that would be very, very, very close to 0. And that's what happens much of the time, is that I do get an asymptote here at y equals 0 as I go out to the left-hand side. And that's a significant feature of our logistic curve. All right, so hopefully you got the idea. It's just another type of function. It's an exponential function that's been put into a rational function. The combination of the two gives us this interesting situation where I have a asymptote as I go to infinity and also a different asymptote when I go to negative infinity, and that allows us to model this situation where there's some type of carrying capacity. All right, go ahead and work a couple of questions just so you got a little bit of experience with it, and then we'll be done with this topic.